We're going to continue talking about relationship between nucleophilicity and basicity. So in a previous video, we saw that we have some species that can be strong bases and a strong nucleophile. An example of that, we have, I don't like that marker much. We have ethoxide. That's the conjugate base of ethanol, very strong base. We also have methoxide, and we have hydroxide. So these are examples where there is a correlation. So strong base, strong nucleophile. All of these are conjugate bases of weak acid. Now we have other species such as tBuOK. This is a conjugate base of tRibutanol, so it's a strong base, but it's a weak nucleophile due to a lot of steric hindrance. So because it's a big, bulky base, so we're going to say this is a strong base, but it's a weak nucleophile. Okay, so my light was a little low. Let's say it again. So correlation, strong base, strong nucleophile, we find in ethoxide, methoxide, and hydroxide. And this is different. This is due to steric hindrance, the bulk. We have that this is still a strong base. It's a conjugate base of weak acid, tRibutanol, but weak nucleophile due to the size. We also saw other examples of bulky bases in triethylamine or diisopropylamine. We saw that example before. Other examples of that are a couple of bases, DBN and DBU. Those are big bases with nitrogen in ring size, a couple rings fused. So now, but I'm going to talk now about another example of a species that are actually weak bases but strong nucleophiles. And these are halides. So say, for example, iodide, bromide, chloride. These three are the conjugate bases of hydrochloric acid, hydrobromic acid, hydroiodic acid. So all of these are weak bases coming from very strong acids. However, because of the large size, they are polarizable. Say, think of the electron cloud can be distorted. Think, for example, if you have a very large p orbital like that and getting this elongated, being able to polarize one side towards having more electrons, say electron density more to one side than the other, and being able to reach on the carbon. So think about that idea. And so these ions being somewhat large, they are polarizable. And so despite of the fact that they are weak bases, these are weak bases, they are strong nucleophiles. So here we see an inverse correlation in the series above. There was a strong base being a strong nucleophile. Here you have weak bases that are strong nucleophile. And an exception in here is fluoride. Fluoride is both weak base and weak nucleophile. And it is because of the size, this very small atom. So it belongs to the same period of carbons. So second period of the periodic table is not as polarizable, so that makes it a bad nucleophile. Other species that we can mention about polarizability is, say, for example, the difference. If you consider water and OH, we know that OH obviously is a strong base. OH is a strong base, a strong nucleophile. Water can be nucleophilic, but it's weaker. So we can say here water is a weak base, weak nucleophile. Here, hydroxide is strong base, strong nucleophile. Now let's look at the molecule similar to that, so dihydrogen sulfide. And here what we're doing is replacing the oxygen by a sulfur atom, which is in the period right below, so much larger. So it turns out that this acid is much weaker, stronger, I'm sorry. So the pKa of water here, say pKa of water is 15.7. pKa here is about 7, so much stronger acid. So that makes this base weaker. So it's a weak base, but because of its polarizability, being a larger atom, is a strong nucleophile. So again, here we see an example of a weak base that is a strong nucleophile. And notice here, OH was a strong base, strong nucleophile, and this hydrogen sulfide is weak base, strong nucleophile. So notice that, and the difference is the size of the atom, polarizability. And the fact that we know is weak base is because it's a conjugate base of a stronger acid. And I'm saying relative, I'm comparing the hydrogen sulfide with water. And so with this, we should be able to now recognize, now when we see a reaction, we should be able to recognize if that reaction is likely, for example, to undergo a nucleophilic attack or have a proton transfer. For example, if you're using this reagent here, because it's a weak base, it is unlikely that it's going to act as a base. It rather do a nucleophilic attack. In the case of hydroxide, that is both a strong base, a strong nucleophile, you can have two things going on. So you can have a nucleophilic attack or a proton transfer reaction. And that's essentially what's going on when we have the competition between substitution and elimination reactions. So understanding these species, nucleophiles and bases, is critical to understand your reagents and what is that they're doing and to be able to predict products in a given reaction.